We're streaming live on YouTube. Well, good evening, ladies and gentlemen, and welcome to this June meeting of Astronomy Ireland. We're delighted to have Dr. Meg Schwam from Queen's University in Belfast joining us this evening to hear our main talk, Tales from the Solar System. I'm David Moore, the founder of Astronomy Ireland and the editor of Astronomy Ireland magazine. Our format for the evening, for those of you who are new to them, is a little bit about the past, what's been happening since our last monthly lecture. Then, of course, the present, our main speaker, and then a little bit what's going to happen in the future. So what's happening between now and the July lecture, which I'll tell you details of at the end. So do stay for that as well. There's going to be plenty of sights to see in the sky. There always are. So that's it, past, present, and future. So let's get on with it. Welcome to everyone from all around the 32 counties, and indeed around the world. I know we have one or two international viewers. We've been very popular over the last year. During the pandemic, people have turned back to a lot of their hobbies, including astronomy, with a vengeance. We've nearly doubled our membership in the last 12 months, which is great to see. You could travel trillions of kilometers while everybody else was restricted to 5 kilometers, which was great fun. It was actually our 30th birthday year in the past year. We founded Astronomy Ireland in 1990. Since then, tens of thousands of people have joined the club, and we have become the world's most popular astronomy club. And there are even more people who follow us on all of our social media channels. Let you look at the website to check those out. Make sure you do follow us if you're on social media, because we can do daily updates of things like satellites and lots of other things as well. In fact, that's a little bit about what we do. We publish Ireland's only monthly magazine, Astronomy Ireland. Let's see if we get this on screen here. There we go. This is the June eclipse issue and the July issue. It's being sent to the printers this week. So hopefully you'll all be getting that toward the end of next week in the post. If you're not a member, you can always join at astronomy.ie 24 hours a day. If you are a member, do get all your friends and family to join. The more the merrier. We want to keep that spot as the world's most popular astronomy club. We send out a weekly email to all of our members to remind them what's happening in the sky, and also to tell them about anything new. There's been a bit of a nova in Cassiopeia that we've been tracking over the last few weeks, which has been great fun. The other thing we do, of course, are these lectures, which now are online for everybody in the 32 counties. We are a 32 county organization. We have members scattered all across the country. Relative to population, Dublin isn't even the biggest or most popular county that we have. So no matter where you are, you can certainly join in these days, thanks to everything being online. There are public watches, and we even stream those live online. We managed to stream part of the eclipse last week, which I'm going to tell you about in a moment. Our big annual barbecue under the stars, Starbecue, is Ireland's biggest annual star party. That's coming up on September the 4th, and we're really hopeful it will go ahead as restrictions are relaxed. And more of that, though, a month or two closer to the event when we know for sure. We do talks in schools, including online. We've been doing those right through the lockdown and all the restrictions. So if you're involved with a school, do get in touch. We'll give a talk about the whole universe. And we maintain a huge media presence, as you've probably noticed over the last week or so. There's also our social media channels, that weekly email. So we'd like to keep people informed about what's happening in Irish astronomy all over the country. So what's been happening since the last lecture, which was our May lecture, given by Paul Evans of the Irish Astronomical Association. That was on the 10th of May, and we've been very popular with the media since. I know we've been on radio for things like the new missions planned to Venus, but of course the big one was last week when all hell broke loose because of the deep partial eclipse that we had. Now that's going to be the subject of a huge feature in the July issue of our magazine, rightly so, because there hasn't been an eclipse deeper than last Thursday's eclipse since 2015. There were other eclipses visible from Ireland, but the last time we saw one better than this was 2015, and the next time we'll see one better than last week's eclipse will be in 2025. So we have this 10-year gap where in the middle we have this June eclipse of this year. So we made a big deal about it. The weather cooperated a lot of the country. Looks like the southeast didn't fare too well, but everybody else seems to have gotten a glimpse. I've actually got a bit of eclipse burn, sunburn from standing out for, I say, most of the 2.5 hour event that we streamed from our headquarters in Dublin was sunny, and I paid the price for that, for getting my sunscreen, unfortunately. Hopefully everything will be okay. But hopefully you got to see it as well. We managed to get another shipment rushed over from California of these eclipse glasses. We had told members about them weeks ago, and they had sold out very quickly. So hopefully you all got a pair of those and were able to watch the eclipse in safety. There were lots of other methods in the magazine. Pinhole methods, very simple. A couple of sheets of paper is all you needed to see that in safety. And lots of people send in all kinds of photographs using that method. If you know a bit about how to do it safely, you can project an image, get a really sharp view on a piece of card or white paper. Some people did that as well. There are loads of other techniques. There will be another eclipse of the sun visible from Ireland next year. It's in October, but whereas we had about 40 to 45% of the sun's diameter covered by the moon this time, we'll only have about half that next time. So it'll be good, but not as good as this one. So we're sure to make a big song and dance fuss over that one as well. We were extremely popular with the media. I did television reports for the BBC, for RTE. We unfortunately had so many requests, we had to turn down Virgin Media. Our apologies to those. They only tried to book us on the very day itself, unfortunately. But we also spoke on every other national radio station in the country and a few abroad, and dozens of local radio stations. If you want to hear any of those, if you go to our website and look up the audio reports, or just type in astronomy.ie/audio, you'll hear loads more about eclipses in the past and in the future, from how they explain why we're not talking Greek at this moment, and we're not talking Latin, and why the Middle East problem is all caused by an eclipse, and lots of other things as well. Chinese astronomers being beheaded, loads of great stories. Do check out astronomy.ie/audio. I must have done 50 to 100 different radio interviews last week, and so did a few of our Irish language speakers and other people as well. So it's been great fun to see this level of interest. Loads of people joined Astronomy Ireland, lots of orders in for the eclipse issue of the magazine, the July issue. That's going to be coming out next week, as I said. We also had the end of the International Space Station and the Starling satellites flying over since our last lecture. And that nova as well in Cassiopeia doesn't seem to know what to do. Normally a nova, a new star, flares up in brightness and then dies away. This one did that, but then it had an upsurge again. And it went up on the rise again, seems to have plateaued at the moment. And we'll tell you more about that each week through our email. You can certainly see it in binoculars. I managed to glimpse it at one of its outbursts with the naked eye. And it's up all night long because it's in Cassiopeia in the north sky. It's what's called circumpolar, visible all night long, goes around the pole star. That's a very rare event. I think the last time we had a nova this bright was 2013. So we're talking about a once in a decade event. If you don't know how to find it, do learn. There's always details in those emails that we've sent out before. So that's the nova as well. The Irish astronaut that the European Space Agency are looking for, okay, they're looking for a European astronaut, but hopefully it's going to be Irish, or one of them are going to be Irish. They extended their closing date, and we will tell you about that. So hopefully you've all got your applications in now, and we'll be seeing some Irish astronauts in the not too distant future. So that's what has been going on since the last lecture. As you can see, we always keep very busy. But tonight, we're delighted to welcome Dr. Meg Schwamm from Queen's University, Belfast. She's a lecturer there. Her research focuses on how planets and their building blocks form and evolve. So she's applying ground-based surveys to probe the solar system's many small bodies. She's also involved in the Planet 4 citizen science projects, which enlist the public, that's you, to help study seasonal processes on the Martian South Pole and map the distribution of ridges on Martian mid-latitudes. An even bigger, more prestigious task, in my opinion, is that she's on the co-chair of the Rubin Observatory's Legacy Survey of Space and Time Solar System Science Collaboration. And of course, the Rubin Observatory is going to scan the skies like no other telescope has done in history. And have someone on this island involved in that project is absolutely fantastic. I'm sure she'll be talking to us about that in the not too distant future. That's, I think, a one or two, maybe she'll talk about it herself. It's a $1 or $2 billion project. There aren't too many of those in ground-based astronomy. In 2017, though, Meg was awarded the Carl Sagan Medal for Excellence in Public Communication in Planetary Science by the American Astronomical Society's Division for Planetary Science. So we couldn't think of a better person to get to tell us all about tales from the solar system and making our first talk to Astronomy Island. Please give a warm welcome to Dr. Meg Schwal. Over to you, Meg.
Great, thanks. Just to get a time check, how long do you want me to go for?
Well, typically 45 minutes, but give it plus or minus 10 minutes, and we can leave 10 or 15 minutes for questions at the end.
Excellent, thanks. All right, so let me share screen. It's great to see everybody. Virtually, of course. I wish we could do this in person, but I think this talk is well suited for an online audience. So I'm going to be talking about really tales from the solar system. And I mean tales, and that this is a choose your own adventure talk. So I thought, given the online nature, it's fun to actually let you all decide. And so in a second, I'll have you go to the poll, but the idea being is that you have these options for talks. So we can talk about thinking about, go back one. There we go. We can talk about the telescope that will revolutionize our understanding of the solar system, interstellar visitors from beyond, exploring carbon dioxide geysers on Mars, or the Comet Gateway. And so we probably have time for one, maybe two of these in the time frame. So the goal is, if you go to this link, it is in the Zoom chat, but others can go there as well from YouTube. So if you go to this link, I'll hold it up for a second, and then stop sharing and share the rest of my screen. The goal being that you should hopefully be able to see what people are voting for. All right, so I think you're seeing this now. So far, it looks like the telescope that revolution of the solar system is winning. It seems like the Comet Gateway is also potentially interesting. People seem to like interstellar objects. Gonna give you another minute or two, maybe another 30 seconds, actually. Now, somebody wants to hear about Mars. Or maybe no one wants to hear about Mars. All right. So I think we'll call it. So we have telescope that revolutionized our understanding of the solar system and interstellar visitors from beyond. So I think I can get those two in the time frame. So I'm going to start with the telescope that will revolutionize our solar system, and then move into interstellar objects, because I think those are, it's a nice segue into one to the other. All right, so the crowds have decided. And if you didn't get your favorite topic, just talk to me about it in questions, or invite me back to give a different talk. That's also possible too. Can always give the other two. Okay, so let's talk about the legacy survey of space and time and the solar system. So this is that billion-dollar project that was being mentioned earlier. So what's exciting about this survey is that it is not yet happened. And so I spend a lot of my time sort of worrying about this as I go to bed, of like, how best are we going to be able to explore the solar system with this survey? So the Legacy of Survey of Space and Time, LSST, is going to be run by Rubin Observatory. So Vera C. Rubin, it's named after her, who the astronomer that helped identify dark matter in galaxies, by seeing that the rotation curves for spiral galaxies wasn't changing as it was flattening out as you and didn't behave the way you'd expect if there was just all the matter you could see that was illuminated. And so this survey is named after her because the idea is it's really exploring all different aspects of our universe, our solar system. And so what's really exciting is that this is going to be the largest field view of camera ever stuck on a basically 6 to 8 meter telescope. So effectively, LSST can see this 1.7 square degree field of view. So just showing the moon there for scale, and then you can see on the right here, sort of again, seeing over here, this is sort of the revolution looking at Earth, and like you can see a golf ball. sort of down here. So taking some satellite image, what kind of resolution you would get, right, using this telescope. So it's just amazing, right? We're 1, 2, 3, 4, 5, 6, 7 full moons across and vertical, right? So this is the largest field of view camera ever built, stuck on a 6 to 8 meter glass telescope. And so why this is exciting is that it's going to observe the sky every few nights in 6 broadband filters. So effectively, we're going to get a movie of the sky every 3 days for the observable sky that's visible at that point. And so this telescope's being built in Chile. And so from about 2023, for 10 years after that, it's going to be surveying the sky, looking for moving solar system objects, looking for, supernovae and novae that are going off, and looking at all different things and studying galaxies and their properties by imaging in these filters. And so what this is going to do is that most of the surveys that have studied the solar system have used basically 4-meter telescopes and smaller. It's the thing, if you want to do big surveys, you got to get telescope time. It's very hard to get the biggest telescopes to do big surveys because there's so much science you could do with them, right? Everyone's sort of competing. And so Rubin Observatory is built to be this big survey telescope. And so we're going to get an order of magnitude more solar system objects. I don't even know how to plot this, the number of objects we're going to get, that I'm hiring have a summer intern starting next week that's going to write a software package to visualize these things, because we don't normally play with these kind of numbers. So let me give you some statistics here. So we know about 600,000 main belt asteroids. We're going to find 6 million, basically, by the time Rubin Observatory ends the LSST survey in the 2030s. So I study mainly the outer solar system. And so we know about 3,000, 4,000 known objects today with secure orbits. Okay, we're going to get about 40,000 of those. So I can't in my head sort of picture 40,000 from 4,000. Like, it's just so much more objects, so many more things that we can study. And because it's being monitored, right? We're going to be able to look at cometary activity. We're going to be able to look at how their brightnesses change over time. So as these things rotate. So it's not only just finding them, we get to study them because we're monitoring them. So new comets and seeing how them evolve, right? So again, we're going from a few 1,000 comets to 10,000. And interstellar objects, which we'll talk about in the next section, right? We go from about 2 that we know of today to 10, which even with 2, you call it a sample. With 10, right, you can actually start doing some comparisons. So this is going to blow everything we know out of the water in terms of the known inventory of the solar system. And so, there will be these 6 broadband filters where there'll be hundreds of observations per object by the time you get to 10 years. And so it's really coming. About fall 2023, if all things go right this summer, with finalizing construction of the telescope, this will come online. And so this is October in 2019. This is actually showing that the dome structure rotates. So it's looking and starting to feel like an observatory, and the telescope is being constructed. So this was in 2019. They were putting on the dome vents, the first set of dome gates. They started to install the telescope. They were working on coating the mirrors, or starting to think about coating the mirrors. So the primary mirror, the M1 and 3. So this thing is so wide field that it actually has light go from the primary, which is roughly 8 meter diameter, go up to a secondary telescope and back down to a basically carved out part of the primary that basically acts as a tertiary mirror. And so effectively this 8 meter telescope is about a 6.5 meter, but we'll take it. And so the secondary mirror was coated in silver at the Summit facilities installed chamber coating station, because everything's got to be done at the Summit in Chile. So everything from building the telescope to the coating chamber for the mirrors, right, all that's being built at the Summit. The camera is 3,200 megapixels, so it's way more than's in your smartphone. It's again sort of the widest field high precision imager we have in the optical being stuck on a telescope, and that's coming along too. So if you like your romesco broccoli, this is the image for you. This is the science validation sort of images in the lab for the camera. So this is the assembled science grade camera, and they stuck romesco broccoli in front of it and took some photos, and you can just see the resolution here. And so yes, this is up close, but like it's beautiful to see all the components of that imager, right, coming in with crisp quality. And so in December 2019, the dome cladding was finished. And this is what it looks like as of a few weeks ago. The front end of the telescope was installed. The construction was shut down completely for many, many months due to COVID. And so it's really nice to see that construction has restarted at the summit with a very limited crew, but they are up there working on this, finishing assembly of the telescope and working on the internal structure of the dome and remaining construction tasks. And then that'll lead to installation of the commissioning camera, and then eventually that camera that generated these images. Okay, so why is this interesting? I think I just want to show you a little bit is that what you're seeing here is a simulation of what the LSST survey could look like in terms of observing on the sky. So this is sort of looking at the night sky, right? The whole celestial sphere, right? We're telescopes in Chile, so that's why you can mainly see the southern hemisphere and can't get parts up here. The idea being here is that we're showing what the sort of full survey looks like over 10 years. Here we're looking at what it does on a nightly basis as it runs. Right, and what's the cumulative as you build from each day, right? What are you building up towards 10 years? And you'll see there's all these different structures within it. So the reason we're covering this portion up here, this is part of the northern ecliptic. So the ecliptic plane kind of comes around here. So for people like me, we want to make sure that gets observed too, because that's where a lot of our solar system objects are. You'll notice these very sort of more brightish points. Those are deep drilling fields. So that's where the telescope is coming back more often to get more observations. And that's being driven mainly by galactic and extragalactic science. And so the idea being is that we don't fully know what this cadence is going to be yet. I'm on the committee that's helping to recommend what the final cadence will be. There's some sort of baselines of things people want to do. And so we're seeing what ways we can optimize that, or maybe the best term for that is evenly distribute the unhappiness among the whole key science groups and communities that want to use this telescope. So the idea being to cover as much sky as possible and many of these filters, but exactly how we do that may depend slightly just to maybe enhance some of the science. So obviously, right, doing up here is more for getting solar system, doing these are more for the galactic or extragalactic science, and people that are studying the galactic plane, right, or looking for microlensing events will be looking in these areas. And so we're figuring out how to exactly optimize this. But I like this because this video because you can kind of get a sense for what's going to be happening every night. So the really cool thing I think about LSST is that it's providing the finding of moving objects. I spent my thesis looking for objects in the outer solar system, and I had to blink the images and help write the moving object pipeline. And so built into this an effort to construct the telescope has been a very long period of time of developing the software. So on day one, everything's ready to go, which is really exciting, right? So no one's trying to write the analysis software after the data's come in. This is happening in real time, right? But that as they're constructing the telescope, they're building the same software. And so for us in solar system, there's a lot of interesting data products. So one is every solar system detection is public. These will be made public to the Minor Planet Center, which is the gateway, the clearinghouse for solar system detections that catalogs them. And so I think that's really exciting that anyone who wants to know what Rubin Observatory is finding will be able to see that by going to the Minor Planet Center and look at the new lists. So the idea being here is that every night there are real-time alerts that are coming in. So 60 seconds after the camera shutter will close, any sort of transient source, basically that's in the images, will be identified and sent out in an alert stream to let the astronomers know, and amateur astronomers and anyone who's interested, that there is something that is different in the image. That could be a solar system object moving. It could be a supernovae, for all we know, right? An astrophysical transient. If it's a known solar system object, so if it's an object on a secure orbit that we've observed before, or eventually that Rubin Observatory and LSST has seen before, the software will link it and tell us. And so it'll say, this is Eris, or this is asteroid with its number, right, that's been found in the image. If it's new, it'll take a few days, and the solar system processing pipelines will look and link the new objects. And so you'll get on a daily basically sense or scale That new detections will be processed once there's 3 observations. So Rubin should take 2 images on a night so that we can detect the motion, look for objects that move between those 2 images. And so these software pipelines will look for that pair and see that something has moved and link it, and then take those linkages, or tracklets as they're called. And when it finds 3 sort of 3 tracklets separated by no more than a week, rather 14 days, so 2 weeks, it'll try to fit in orbit. And if it can identify an orbit, then it's declared a new object. So we'll also be getting new discoveries, and those will be sent to the Minor Planet Center once the software can go, I think that's a moving object. It'll send it to the Minor Planet Center, which will do a better job at fitting the orbit and come back and say yes or no. And so all of this will be in, all this information will be stored in the public clearinghouse that is the Minor Planet Center. So even if you don't have proprietary access to the data, there will be, anyone in the world could be able to see what discoveries in terms of solar system objects are being discovered by Rubin Observatory. So it's going to be really exciting in the first several years, because we're going to find most of the inventory of objects, and then more, most of the stable populations. So the asteroid and Kuiper belt, but comets and near-Earth objects will continue to be discovered throughout the 10-year survey. So it's a really exciting time that, like, as the data is coming in, right? Basically, within a few days, we're starting to find objects and have them report their discoveries reported. So what can Rubin Observatory do? It's going to help discover near-Earth objects. So this is just showing some predictions for completeness in terms of year of the survey. This was assuming it started in 2022. It's now a little bit delayed. And just saying that, like, Rubin Observatory plus other observing capabilities gets us to buy about 2030 to 73% of very small near-Earth objects. And same thing for potentially hazard ones. These are ones that potentially could hit Earth. These are, things that people, astronomers are monitoring because they potentially have orbits that could intersect Earth when Earth is there. And about 81% of the ones that we're really worried about, that would be city impactors, right? City destroyers we'll know about by using LSST plus the known resources that are observing now to find young asteroids. So there will be, will help with that problem, right? To really identify, things that, and track and catalog things that may hit the Earth. The other interesting thing is that we know about main belt comets, or called active asteroids. And so we sometimes notice that if you observe or monitor asteroids, you sometimes see them have tails. Or in this case, it looks like an X pattern, and that looks like it was impacted, causing a dust trail. Sometimes you find them to completely break apart. So you're observing and it looks like there's dust coming off of them. And then you observe later and it's no longer there. It's been a shattering event. So either it broke apart because it started to rotate too rapidly, collision or something else. And then others seem to repeat in this process, and that we think maybe those are actually sublimation of water ice. And so the active asteroids seem to be in those 2 categories of main belt comet, which looks like there's some water ice buried or hidden in your surface as an asteroid, and then you start sublimating it close to when you get to your closest approach to the sun. And then, you could move away and go to your furthest point, or perihelion, and that activity stops. And that these other active asteroids are really just things that have had collisions or have rotationally spun up. And so there's this interesting, trend now that there's only about a handful, we know a few handfuls of these objects. So we know about 20, 25, maybe 30 now active asteroids or main belt comets. And what's interesting is that we notice that there's some correlation with their orbit, with where it's pointing in terms of, like, Jupiter. And so all the objects that have, we think, repeat activity that's due to water ice all seem to sort of align with Jupiter's orbit. And we don't 100% know why. Now, there's not that many of these main belt comets, so that we need more objects to really be able to say, is that correlation true? And so LSST Rubin Observatory is going to be able to give us that, because we're going to find, 5 million asteroids. So just think even a percentage of them are these main belt comets and active asteroids. We're going to be able to monitor them and be able to start following up as we see activity to decide whether or not it's something that's had a collision or rotationally spun up, or whether it's, we think more comet-like with sublimation of water ice, and really explore whether that orientation with Jupiter matters. And there's something about the history and origin of these objects linked to Jupiter's orbit. We're also going to be able to test whether or not there's a planet 9. There's still a lot of debate in the community about whether or not there's a need for a 9th planet beyond Neptune. That's, something like a mini Neptune or super Earth that is causing an orbital alignment of very distant orbits. These objects shouldn't be aligned. The only thing that keep them aligned most likely could be a planet. There's some other mechanisms, but the most likely culprit would be a planet orbiting on an eccentric orbit or planetary mass. The problem is that there's a lot of biases that have been introduced in observing from different surveys. And so there's right now some surveys that don't see the signal or not sent, and there are others that are proponents of this that claim those surveys are biased and couldn't see the signal, and therefore that's why they're saying they don't see the hint of a giant planet. The beauty is that Rubin Observatory is observing both all of the northern ecliptic sky of the solar system and the southern ecliptic. And so with the survey that's is surveying several, all of the observable sky every 3 nights in multiple filters for 10 years, if there's a 9th planet and it's actually observable, and the current predictions do have it being at a magnitude that could be detected by Rubin Observatory, it's either going to be found because we're directly going to see it, or we're going to find more of these objects and decide whether or not we start to see ones that are sort of have an alignment that varies over here and over here and over here in these different directions that would argue against there being a planet. And so is it just that we're all, by all the biases that are in our surveys, we're looking in periods of the sky that preferentially, right, is where these things would appear. And so with Rubin Observatory, we're really going to be able to answer that question. We're going to find more of these objects that are going to tell us with the pointing history and everything about Rubin Observatory about what's going on. So I'm really excited about that because I think trying to figure out whether there's a 9th planet beyond Neptune is really interesting. It has a lot of implications for the formation of our solar system and its evolution. And so either stay tuned, we'll either see it with Rubin Observatory, it'll be directly there, or we'll find enough objects to decide either way whether or not the influence from a 9th planet is needed to see what we're seeing for the orbits. So this we'll talk about in the next section more about interstellar objects, but I'll give you the brief story here before we dive into it, is that interstellar objects are objects from other solar systems that are passing by and have, and are feeling the gravitational well of our solar system. And so we know of 2, and I will give you all the scoop about these objects. And so because Rubin Observatory observes so much sky, it is going to be able to hopefully find a few more of these, hopefully at least 1 or 2 a year. So by the fact that we found 2 Eyed Borisov, sort of in a short period of time, since the discovery of One Eye Oumuamua, the hope is that we're going to get a whole bunch of these to start being able to study. And that's really cool because the 2 we have sort of started to tell us some interesting stories. And I just want to talk about there's some cool synergies with ESA missions. So I don't know if you've heard about ESA's Comet Interceptor mission. I'm on the science team. It's a really cool mission. It's an F-class fast mission. It's going to be launched with a few spacecraft, hopefully in around 2028. And it's going to sit at this Earth-Sun Lagrange point, L2. It's basically going to hang out until there's a comet to go to. So right now, we don't know of any target that Comet Interceptor is going to. So they're launching this thing without a known target, because the point is we're going to sit and wait to find one that's the best thing that's going to give us the best chance of encounter, right? The best possible comet, with the idea to hopefully find a dynamically new comet to really study something that's coming into our solar system for the first time since it formed. Right, it's been sitting out in the Oort cloud, the repository of long-period comets, and coming in for the first time. And so right now, the best discovery engine for the ESA Comet Interceptor mission is Rubin Observatory and LSST. So with 10,000 comets, LSST will likely find Comet Interceptor's target. So I'm on the target selection team. And so, we're going to have a lot of ground-based and community follow-up. And so it's going to be, once that target's selected, or as we're going through, hopefully there'll be many things that we find with Rubin Observatory that Comet Interceptor could go to and have the real trouble of having to decide between. So I just want to highlight this as something of the ground, the ground-based sort of survey is going to help lead Comet Interceptor to where it needs to go. So I think that's really exciting. And so with 10,000 comets that are going to be discovered, there's a really great chance we're going to find something interesting to send that mission to. And so I just want to mention that, I said that the survey cadence isn't fully decided. What we're doing as astronomers is we're actually arguing amongst ourselves and advocating for what do we do to make this survey the best. And so every science area has had scientists write sort of little proposals or white papers to argue about cadence and what we think is the best. And I'll just highlight that this plot here is showing just some variations on that video I had shown of how LSST would be observing, and just showing sort of these different colored lines or different Kuiper belt comets, asteroid near Earth object populations, the solid lines being brighter, larger objects, the dashed line being smaller objects. And you're just seeing basically the fraction of objects discovered compared to sort of a baseline survey, which I believe is this one. And so you'll notice, that most of these things look okay, and then there's like this big drop. And these are surveys that don't have that northern ecliptic spur part. I showed you that sort of northern part of where the ecliptic is. And so again, this is what a lot of us have been doing, or I've been doing, is trying to make sure we advocate to remind our galactic and extragalactic collaborators and friends, and the Rubin Observatory Cadence Committee of just thinking about that this is, that this is a huge drop. We lose 30% of the outer solar system population discoveries if we don't observe that northern part. So the idea being is right now, this is the community is doing, is sort of looking at all these different tweaks and variations on the survey cadence and deciding what we're going to do with it. And, and recommending, in our own sense, what to do. And the Rubin Observatory has this committee that I'm on, amongst others, to help sort of take and synthesize that information and make the best sort of cadence. So stay tuned. We're really going to be able to discover and know so much from the survey, And so it's going to start in about 2023, if all goes well with finalizing construction of the telescope. So all I can say is stay tuned. There's going to be so much more that we'll learn from that in the coming decade. So I know it looks like I can see 2 comments. So are there any questions, burning questions anyone wants now before I jump into interstellar objects?
Maybe one quick question, Meg.
Sure.
Very near-Earth asteroids that pass very close to the Earth, they'll be moving very, very fast. Is there any kind of limit on how close they can be or how fast they can be, or has anyone thought of that? You don't want one that's going to pass a few thousand kilometers above our head and it leave too thin of a streak.
Well, so I mean, I think the fast limit just means it's streaks. But you can identify streaks in the images. So as long as the detection algorithm can identify it, and as you streak, you divide the light out, So now it's not like a point source. So your detection limit changes in how faint you could see or how small of an object. But on the most part, because we're taking 2 images, the survey will take 2 images a night. A bunch of those should be okay. And then also the idea is there's people advocating in twilight time that that's a really good time to point near sun to find things that you wouldn't be able to find during the night, and that will have a shorter cadence. So on the most part, it's okay. And then also we still have those other surveys around that are going at shorter cadences. So it's the idea of having Rubin plus all these other assets that, again, make sure we can all sleep tight at night about an asteroid impact.
What's the exposure time?
It's 30 seconds roughly.
Yeah, same as Atlas.
But yes. All right, any other questions? I can't see the chat, so if there's questions there, do let me know.
There's just one from Tom Finnegan there, Meg. Is it possible that the mass is a mini black hole? Maybe you've already answered that.
It's possible. There's a really nice paper on it that actually draws the the size of a black hole, smaller than an A4 piece of paper. We can't rule it out. But I'm always a fan of Occam's razor. Like, what's the simplest solution? So how do you get a mini black hole there is even harder than how do I get a giant planet out there? So it could be, and we can't rule it out until we rule out all the observational things. So, right, if we don't see the planet should be in a lot of parameter space of the types of surface it could have, right? Whether it's a gas giant or if it's rocky and it had volatile ices or whatever on its surface, we have a range of ideas of what the magnitude be. So it should be visibly seen moving in the Rubin Observatory images. Might be hidden in the galactic plane where there's lots of stars, so that might make it a little harder. But if not, we can use the detections from the objects that are out there as well. So that in that case, it would be harder maybe to rule out the black hole. So it's definitely a viable option, but it's sort of one of those lower down the list because it's high. It's to capture a black hole that's in orbit and have not destroyed an Oort cloud. Means it had to be captured before the giant planets moved and things like that. So it's possible. It's definitely possible, but given we see our long period comets, and that it's way harder to capture a black hole and keep our solar system intact. It's lower down on my list, which is why I don't mention it, but it's a very, very valid point that it is real. It is a real possibility given the mass dynamics.
Okay, and Mick Dunn has just asked there, what is your role in the Comet Interceptor mission?
I'm on the science team, so I'm doing none of the heavy lifting. It all goes to the PIs and so the rest of the science team and engineers. I'm also on the target selection team, so I'm helping give some perspective about what Rubin Observatory is doing in terms of, as somebody who's going to use it for my science, right? About how we might help find a target, right? So I'm helping to be on the team with many others, including Garrett Jones, who's the PI of the mission, and Colin Snodgrass, who's deputy PI, who are doing all the work and really made this thing happen. So I have a tiny role on this mission, but I'm still excited about it. All right, so I'm gonna go and talk briefly about interstellar objects because I feel like it's always a good place to end. Okay, so we touched on interstellar objects. And I like this saying, the solar system is a nice place to visit, riffing off that line from the Twilight Zone, if you've ever seen that episode. That interstellar objects, as I sort of mentioned briefly, are things that are actually stuff that formed around other solar systems that have been expelled and are floating around interstellar space and happened to find the sun's gravitational well and fell in, and we were actually got bright enough that we could see it. And so there have been predictions that this has been true, but we've never seen them until Oumuamua a few years ago. And so Oumuamua was discovered by the Panzers Telescope in Hawaii. So it has a Hawaiian name, which means a messenger that reaches out from the distant past. I love the name for Oumuamua. I really think that sort of describes interstellar objects. So this is the Panzers Telescope. It's a 2-meter on Haleakala in Maui. And so this has been serving the night sky. It's one of their precursor surveys to LSST, looking for near-Earth asteroids now, also looking for supernovae. And so they found Oumuamua after it had already come into the solar system and fell in. And so we actually it was discovered right already after it had passed perihelion and was on its way out. So you can see here from the predictions, right? It came in pretty bird's eye view down, and then sort of came to interacting with the sun, right, and changed its orbit. And so the cool thing about this object and why interstellar objects are so cool, I think, is that, right, I've been spending my time studying the outer solar system, and we use all these ground-based techniques and space techniques of studying photometry and light curves and how the object changes in brightness to get an idea of its shape. Right, using spectroscopy to try to understand what's on its surface, right, using every tool, sometimes even sending spacecraft, right? And so now we have the ability to, like, those planetary disks and things you've seen in, you know, images from other solar systems, right? We're actually able to take a piece of some other solar system and throw the same things at it that we use in our own solar system and compare them, right? And so, you know, just looking at our solar system populations, right, we're now able to start looking at it and saying, how are these things different or similar? I mean, that's what I think is really cool, right? This is just showing the inner solar system in the asteroids, right? Just showing their orbital sort of depiction, right, amongst the giant planets, right? And so we know of enough objects, right, to do some comparisons and say, hey, look, what do these objects look like compared to our own? So with Oumuamua being discovered, right, this started to kick off that discussion. And how do we know that this object is interstellar? It has a hyperbolic orbit, meaning that it has an eccentricity much, much greater than 1. So new comet, dynamic comets also have an eccentricity of about 1, but this is much greater than 1 is your first sign that this thing is not from our solar system. It is incredibly hard to create a hyperbolic orbit unless you've had an interaction with Jupiter. And we know that this object didn't, because when it's been dynamically integrated, it came in this way and turned around, right? So it had no interaction with Jupiter. So we knew that this thing, once it was announced that it was hyperbolic, that this had not interacted with Jupiter and had to come from some other solar system. And what helps kick this off is that if you look in terms of velocity, right? So these are just different velocities, X, Y, Z, effectively in the galaxy. There's Oumuamua, and it hanging around with all these other, has a very similar velocity to a whole bunch of other background stars in our solar neighborhood. So it could have come from anywhere, but it looks pretty good. It came from somewhat, you know, it has velocity that's consistent with being anywhere with any sort of star around, and, you know, coming from any of these stars in the solar neighborhood, or even having, you know, passed through them and sort of had its trajectory shifted, right? And so that's, you know, that's really exciting that just from its orbit and its velocity, right, that this is, you know, this has been able to be said. Like, it really does look like it's coming from the solar neighborhood. And I want to point out that not everyone realizes that our entire solar system sort of reorganized itself, or at least the mid and outer solar system did. And so Jupiter, Saturn, Uranus, and Neptune, and a probably likely 5th ice giant, sort of were scattered, moved around and shifted their orbits by scattering planetesimals, which, and so really our solar system is really messy. The way I like to think about it, it's like giving a toddler a cookie. And yes, you know, they get most of it in their mouth, but there's a whole bunch of it, or maybe half the cookie is on the floor in crumbs. And the same thing as our solar system did, right? It had all these planetesimals, but there was an interaction, right? The giant planets interacted, scattering these planetesimals. Neptune, Uranus, and Saturn moved out. Likely an ice giant even got ejected, and Jupiter moved inward. And what that was doing was it also scattered out a lot of planetesimals out into a Oort cloud, out into the Kuiper belt, and out into interstellar space. So this is just showing a simulation of that. And so this is, you know, really exciting in the sense that, like, Jupiter and Saturn probably crossed mean motion resonance, which excited their orbit. And basically the idea being here is that once these orbits are excited, they excite the other giant planets and scatter out this proto disk of objects that created the Kuiper belt, our Oort cloud, and also messied up interstellar space. So in this simulation is about 800 million years. This happens, and it's in a blink of an eye. Once it happens, all hell breaks loose. And there you go. Great. And even in this case, Uranus and Neptune switch orbits. So just showing you this in a sort of slow down snapshot, this is what happens. Right, and so our solar system was pretty messy, dumping these objects out into interstellar space. And so our solar system is guilty of, you know, basically dumping its leftover garbage from the construction of the solar system out into interstellar space. And we just happened to pick up somebody else's trash, right? Just kept flying in. And that's a really exciting bit, is that we've expected this, right? And because this is so rare, almost every telescope around the world was observing it, because there was about a 2-week window that Oumuamua was bright enough that we could have studied it. So these are observations that I helped get at Gemini Observatory in optical and near infrared. And what you notice is that everybody thought these were going to be comets, that we would see a tail. It would be fuzzy, because I just showed you, right, that all the objects that got scattered in our model, right, of the solar system in terms of what we've discovered these days, right, mostly icy bodies are the ones that got kicked out. But Oumuamua doesn't have a tail. It never did. There's some evidence that its pathway, its trajectory has changed a little. And the only way that could likely happen is maybe some cometary outgassing. So it might have at the end turned into a comet, but we had no tail. And we've been able to study its rotation. It looks like basically a flattened pancake or cigar. People have gotten a spectroscopy of it. It looks pretty flat, which is like a outer solar system object. These are observations that my collaboration was able to get. And there's Oumuamua, and here's every like known solar system object, some from our survey, some from others. And so Oumuamua is that star. And so if I had not told you, or you had not told me that star was a object from some other solar system coming inward, I would have told you that that's a typical outer solar system object, sort of Trojan asteroid looking thing, like probably formed from the proto-Kuiper belt. And that's kind of exciting. So I like to say that Oumuamua is vanilla. It fits, it fits within what we know about our solar system. But the cool thing is that Oumuamua is tumbling. It's actually rotating, not along its principal axis. And so one way to think about it, sort of doing this, and sort of changing which viewpoint we're seeing as it tumbles. And that's pretty exciting because that could have been viewed on this object as it was ejected from its own solar system. We don't know, but we definitely see the tumbling. And I like this image to show it because you can see as they repeat sort of the rotation period, you can see that the peaks don't line up and the shapes look a little different, with the red being one rotation period, the same phase, and the blue being another. So very rare for us to see tumbling solar system objects. And so Oumuamua happens to be tumbling. So just mention, is it aliens? It's definitely been brought up in the press a lot because it could be the obelisk. There are no radio signs detected. Also, if it is, it's tumbling. So it's not a really smart obelisk because it's tumbling. So unless they have the lights out, which they could, right? Maybe they were like, somebody's knocking your door and you don't want them, you turn the lights off and close the blinds. Maybe the aliens were, faking it and they're there, but likely it looks like a solar system object, right? This shape and size are at least consistent with what we think in the solar system. It's on the extreme, but we have things like Oumuamua in the solar system. And so it's likely it's a planetesimal. So I'll just end by saying there was two Eyed Borisov came, more than a year ago. And so we had two of these, and this was actually discovered by Borisov, who is an amateur astronomer in the Crimea, looking for near-Earth comets, and happened to spot it. And two-Eyed Borisov is a comet. It has a tail, it's fuzzy. So already these two objects are behaving differently, just like cats, which is exciting. And so again, with LSST, we're gonna get 10 of these or more, right? Getting a few a year. We're gonna be able to see how many more like Borisov versus Oumuamua. And so just to show you that Borisov has a beautiful coma. It's an image I helped take out propose for the Gemini telescope. And the really interesting thing and exciting thing here is that the composition of Borisov is a little different from what we see in the solar system, and it was changing. So we really need more objects to really understand and place it in context, but it's still somewhat, at least there's one more comet in our solar system we know of that's more extreme in composition than Borisov. So I like to say that Oumuamua is vanilla and Borisov is pistachio. Rare, but you can still get pistachio, right? If you go to the ice cream parlor. And so again, I like to show this image just to show you how fast these objects are moving. On the left, it's been aligned from the telescope on the comet using 3 filters. So you can just see everything else shifting as Borisov stays constant. And if you align on the galaxy, right, you can sort of get the red, green, blue from Borisov. So I just like to show this and show you how we really put these images together, multicolored band images together, by doing this sort of shifting magic. And I didn't do any of this. It was the experts at Gemini Observatory that put this together. So again, I'm just going to end by saying, interstellar objects are really cool. There's not a lot necessarily we can say with two, but we can already say that vanilla and pistachio, right? They're looking like some of the extremes of the solar system, but they're still kind of within what we know. So it's gonna be really exciting to see, do we see more that look like comets, more that look like they're less, they don't have a tail, but maybe show some signs of cometary activity, more to come, right? And so I think it's really cool that we're gonna be able to use Room Observatory to help study and really reach out and touch other solar systems and see how they've formed. And so that's all I've got. So I'm happy to take some questions on interstellar objects.
Meg, just one on YouTube. It says, are rock fragments traveling through our planetary system and departing in the depths of the universe can transfer life on their surface like a bee that carries pollen?
There's a theory for that. It's sometimes called panspermia that has happened. That the thought of being in our own solar system, maybe Mars had life and a meteorite knocked life on Earth. Theoretically, in some ways that might be possible, but you also have to have that rock get down to the surface and not burn up. Right, so I think that's such a rare way of transferring things that I'm not sure that that's the most effective way that any life started that way in our solar system or in the galaxy. It's definitely, people are thinking about it. The other theory that's been talked about and some researchers are working on is thinking about, could interstellar objects passing through molecular clouds or other forming system, clouds forming stars or disks that have yet to form planets, could an interstellar object passing through trigger planet formation, right? As it's through that disk, could it trigger waves that start condensing materials? So I'm not sure that life is necessarily going to be transferred that way, but people are thinking about, could it have started other solar systems forming by having sort of those leftovers sort of moving around in the solar system in the galaxy? But it's definitely a thing people are thinking about.
Yeah, and second question there. Recently, I heard that the water in our solar system was formed before the sun itself. Is that true?
Can you repeat that question?
Yeah. So recently, I heard that the water in our solar system was formed before the sun itself. Is that true?
I don't know if all of it did. I think there's definitely some of it that, there are definitely grains from interstellar space, right, that has, incorporated. But I guess in some sense, the water molecules needed to be there. So yeah, they're probably older than the sun in terms of being around in some sense, but the individual components of it were probably around before. But some of that was probably in steam and other things. So exactly how you define what was water, like especially towards the inner solar system. But yeah, I mean, there's an ice line where things start to condense. So I think it's possible some, all the raw materials, we're all stardust, right? We're all coming from originally from large stars and supernovae. So yeah, I'm not quite sure exactly what's meant by that in terms of was actually water molecules around. And so, yeah, we did definitely detect water in other, like our clouds and things. So yeah, I'm sure some of it was there. Also, probably some of it disassociated as the sun was forming and heating up, right? And then came back together. And whether that counts as new or is it old, I'm not sure. But yeah, there's a lot of the raw materials, right, are much older than the sun.
Okay. And Edward Malarkey asks, have we witnessed or recorded objects colliding with the sun or other planets?
Yes, both. Maybe not exactly hitting the sun, but there are sun grazing comets that come pretty close and then get vaporized. We see there, not now, but in the past, Jupiter got hit by a comet. So Comet Levy 9, if anyone remembers that, Comet Shoemaker Levy 9, it came close to Jupiter, got broken up into a string of pearls, basically a whole bunch of chunks, and impacted the surface of Jupiter. I can't remember exactly when that was. I was a kid, so I'm going to say that was like 97, 96, 97, around there. That so 1997, 1996, that happened, I think. So yeah, that was captured, and we're definitely, I think, thinking about Urban Observatory. We want to make sure we track how close objects get to the giant planets to capture something like that. and see how the atmosphere reacts, right? So astronomers got to watch Jupiter's atmosphere and see how it sort of went back to normal and how long it took after the comet impact. So yeah, fingers crossed there'll be something else that hits a planet that's not ours that we can watch.
So Shoemaker Levy 9 collided with Jupiter in July 1994. Is that the one?
Yep.
Yeah.
Ballpark order, correct. So 97, 94. I knew it wasn't 1990.
I remember watching it from one of our watches at the Square Shopping Centre in Tala car park when Jupiter had two big black eyes. It looked like a panda.
Yeah.
Is that the end of the questions, Laura?
Yeah, that seems to be them all.
Fantastic. Well, excellent talk, Megan. I can't wait for this Vera Rubin telescope to come online. It's going to be absolutely amazing. 3.2 gigapixel camera on an 8-meter telescope. Every astronomer's dream. So thank you.
And I just should mention that there's a whole outreach component being built. So again, as you're interested in it, there should be data as well available to the public and lots of ways to help the public dive into. So definitely stay tuned.
Will the actual images that come from it be publicly available? I know the announcements of things found will be, but
eventually they're so big that nobody can download them. So you have to take the processing to the data. But the outreach team, it's a first big observatory construction project to have an outreach component that is working alongside not only the software, but the actual construction of the telescope. So they're planning all these education resources, a public outreach database, so that we won't have all the images, but some for people to explore and dive in, right? Because you want to see the pretty pictures. I want to see the pretty pictures, as well as helping to identify new discoveries. So I'm really excited that basically everyone realized you have to fund outreach too. And that they're working so hard on that to create these platforms to do everything from education tools all the way up to citizen science projects. So I think it's gonna be great for everybody.
That picture you had of the Comet Borisov passing by that galaxy. I love watching new comets that are found to see, are they going to go near something interesting. We've had a few this year. And to be gosh, if we're going to get things like that with an 8-meter telescope, I think we're going to have to reserve more pages in Astronomy Ireland magazine. There'll be a Vera Rubin Observatory page, as well as a Hubble Space Telescope page and a James Webb Space Telescope page. Yep, I think we're going to need a big
problem to have,
isn't it? Well, that's a fantastic point to leave the formal session. Thank you very much indeed, Meg. I look forward to, we certainly will be inviting you back. So many topics to talk about. And welcome to Ireland. I believe this is your first talk to Astronomy Ireland. Met you probably pre-COVID, wasn't it, when we first met?
Yes.
And did you worked at the on Hawaii for how long?
3 years.
3 years. Wow. With just 10-meter telescopes, I suppose, but they're not too bad.
I love all telescopes. They're all useful, right? So they're all their value.
Right. Well, thank you very much again, Meg. And what I'm going to do now is tell people just briefly what to see in the sky and then tell them about the next talk. So I think I will probably take over the, here, I'll just press this video. Too close again. My screen. So I'm going to, in the chat room, oops, I pressed the wrong button. In the chat room, I'm just going to send a link to a book which links in nicely to our next speaker. And if you want to have a look at the chat, you can see that there. In the meantime, let me just briefly tell you what's happening in the sky, because there are some fantastic sights coming up. Just briefly, first of all, what planets are on view? Well, we have Mars in the evening sky, still fairly easy to see. Beautiful sight next to the moon last night. If anyone saw it, it looked like most of the country was cloudy. And it would have been an incredible sight. Mars very close to the moon last night, but it will happen again next month. Venus, very low in the twilight glow. I've seen it a couple of times, but you really have to know where to look. And it doesn't get better as the month goes on, unfortunately. It seems to hover at the same height above the horizon. It will get better as the months go by, though. And then that's the evening sky. If you go to the morning sky, like getting up to the crack of dawn, I think sunrise is around 5 a.m. these days, you'll see Jupiter blazing in the south to southeast. And just to its right, about a handspan at arm's length, to the right of Jupiter is Saturn. Saturn's about a dozen times dimmer. If you've got a telescope, of course, you'll see Saturn's rings. And on Jupiter, don't forget, there are those events where the moons interfere with each other. They can eclipse each other, pass in front of each other. This is very rare, and it's only happening this year. In fact, there is one of those on Friday this week at 6:25 a.m. So it will be in daylight, but Europa is going to eclipse Callisto for 30 minutes. See the magazine for details of that. In fact, everything I'm going to tell you is more or less in the magazine, except for this nova. So very briefly, tomorrow night, Regulus is 5 degrees roughly from the lovely crescent moon. So the moon's not too bright, won't swamp the star too much. That's the naked eyesight. Then, of course, next Monday is the summer solstice. And that's when summer begins in the northern hemisphere. It's at 4:32 a.m. Irish time. Don't let anybody tell you summer begins on the 1st of June. All these things just make you up things that even local weather services like Met Éireann and the like have made up. They're not even internationally recognized. There are formal definitions for this, for the seasons. They go by the solstices and the equinoxes. Summer begins on Monday, the 21st of June at 4:32 a.m. and continues in Ireland until the equinox in September. And we love telling the media that, and they love ignoring us. Then on Wednesday next week, Mars is going to be very close to Beehive star cluster. In fact, you look at the diagram in the magazine, you see Mars passes in front of that cluster. So you should be able to see that in your binoculars. And normally you see the cluster very faintly in the dark sky with the naked eye. A pair of binoculars shows it very easily. Mars is your highlight, it's first magnitude. So you can't miss that. Check out the magazine for more on that. It takes several days to cross it. So hopefully, you know, if not clear on the night, a couple of nights before and a couple of nights after, and you get a great view, a week either side, you should see the two in the same binocular field of view. The day after that, Thursday, 24th of June, isn't the new full moon. It's actually the fourth and final super moon of 2021. So that might make the media. It's probably known as the strawberry moon. And then I mentioned Saturn and Jupiter morning sky. Well, on Sunday, week the 27th of June, Saturn will be a good bit to the upper left of a nearly full moon. That won't be too easy to see. The full moonlight will drown it. But the morning after, actually 2 mornings after, Tuesday, the 29th of June, Jupiter is about 5 degrees, a little bit closer and a lot brighter, 12 times brighter than Saturn. And the moon's a bit dimmer, 77% sunlit. So halfway between first quarter and full. And that should be a spectacular sight. That's worth setting your alarm for. Tuesday, 29th of June. Details in the diagram are in the magazine. And that will bring us then to our next lecture, which is on the 12th of July. And the night before that and the night of that lecture, fortunately after the lecture, so don't skip the lecture for this, you're going to be able to see Mars and Venus near the moon again. So there'll be more details of that in the July magazine, one of the highlights of the month. It'll happen low down in twilight, but it's definitely something to watch out for. The International Space Station will also start flying over evening skies. I have to look up the dates. I think it's July the 14th onwards. It's in evening skies. That's about the time of our next meeting. So I'll tell you more about that then. So that's roughly what's in the sky. Lots more details in the magazine. Do enjoy Mars crossing the Beehive star cluster. If you've got any camera equipment, that's going to be an amazing sight. If only the Vera Rubin telescope was available, take a picture of that. It would be incredible. So before I tell you about the next lecture, remember our evening classes are open for enrollment now. They start in October. Details on the website, astronomy.ie, or just want to go straight to the classes page, astronomy.ie/class. Simple as that. Our next lecture is on Monday, the 12th of July. They're usually the second Monday of the month. And it's going to be given by Brian Harvey, an Irishman who has written several books, world-class books, about the space programs of the world, from the Chinese space program, Indian space program, European Space Agency, and his latest book out this year is European-Russian Cooperation in Space. I've put a link in the chat if you want to click on it and look at his book. You can order it as well. Maybe you might read it before he actually gives his talk about the same subject. And that's happening on Monday, 12th of July, online here. You can book your tickets on astronomy.ie. Just go to the events page and you'll see 2021. Click on that, all the lectures listed there. Pick the July 12th one. Hopefully we'll see you all then. But don't forget to follow us on our social media, Facebook, Twitter, Instagram. And if you don't already get the magazine, do go to the website and order it, because it will tell you lots more about what's happening in Irish astronomy. The next issue is going to be very special. It'll be that souvenir issue of this best eclipse of a 10-year period. So we're going to leave the meeting open for a while. If people want to ask general questions, it doesn't have to be about anything we've talked about tonight. It can be anything. I've got a telescope, how do I use it, etc., etc. There's quite a few people looking in who might help. If you have any questions at all, or just want to have a chat. In the old days, we would all nip off to a nearby hostelry and have a chat late into the night. Can't do that anymore. But we can do it online for a while. So we're going to leave the chat open. So just to close the formalities of the event, thanks to all the volunteers who are working in the background to make all this happen. And especially a big vote of thanks to Meg Schmam for her excellent talk on the solar system, the first of many, I'm sure. Thank you all for looking in. See you next month and keep watching the skies. So normally Mick Dunn starts all the talking. Has he gone? I think he said he had another Zoom meeting to go to. Or anyone wants to ask any questions, just take your speaker off mute and shout them out.
Hi, David. I'm here. It's Anne that has to go to the meeting, not me.
I knew you'd be there.
Yeah.
By the way, if anyone wants to leave now for the meeting, please do. The formalities are all over. But like I say, if you have any questions or even any comments, I mentioned that NOVA. If you don't know how to find it, you could ask something about that. Or
David, did you hear there's another NOVA, a new NOVA in Hercules?
oh my goodness.